All right, in this video, we're going to look at integral notation. So hopefully you remember this notation from the start of our course in calculus. A stands for area under the curve F on the domain from A to B. So in this situation, if this red was the curve F of X, or we can even just call it F, and then A would be here at 0 and B would be here at 1. So it tells us the bounds on the top and the domain bounds. Okay, so to start, we only had the method of the Riemann sum, which says that you're going to break up the interval from A to B into a bunch of little pieces and create a rectangle, a bunch of rectangles. So let's just consider one of these rectangles. So we have a rectangle here. Okay, the width of the rectangle, we often write as delta x. That means change in x. And that's kind of just the distance between this x value and this x value. You could say like x2 minus x1. So how is x changing between this space? And then the height of this would be f of x. So the height of this rectangle comes from whatever this x value is. If I just plug it in, I get out this point on the curve. So that gives me the height of the rectangle. Now, the reason that I need a summation here is because I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 rectangles. So because I have 20 rectangles, I have to do this situation 20 times. Now, because I divided it equally, and you actually could just think to yourself, how big are my 20 rectangles by saying, I took B, I subtracted A, that gives me the distance along here, and I divided it by 20, the number of rectangles. So in general, B minus A over N being the number of rectangles. So that in general actually gives us the width of each rectangle. Again, the height of the rectangle always comes from plugging the value of x into the function. So I would do these over and over and over and over again and have a lot. So instead I'll do a summation. And in my summation, here's my width, here's my base down here, change in x. And then to get my f of x, I just multiply by f of x. Now, as we saw, we did a lot of work with Riemann sums. There's plenty of other videos. We actually can't just plug in x. We have to change the increase. But that's, again, for another video. All right, so now what if I want to find the exact value under the curve? I don't want all this extra space up top. I don't want all this space gone that's not filled in down the bottom. So what I'm going to do is I'm going to take the limit as n approaches infinity. So I'm going to take the number of rectangles to infinity. This means there will be infinitely many of these rectangles. But however, while this is happening, change in x is going to head to 0. So infinitely many rectangles, but their width is infinitely small. This just starts to become a beast to write. And to be honest, we're not going to be able to actually do it with a limit, because what we're saying here is we want to take the limit of an infinite sum. So even if we wanted to use our limit laws and break it up, this summation, especially the summation being infinite, would just cause us to be here forever. If we were going to split it up into term by term by term, we would have an infinite number of terms to take the limit of. So because it gets so wonky, what we're going to do is we're just going to write it kind of as a simpler way and then try to kind of skip over that limit. You could almost think of it when we did the power rule, how we kind of skip over the limit step and we go right from derivative to power rule. It's a little more nuanced than that for the integral. So instead of writing all this craziness, we just use this term here. So again, sigma is S. So I sort of think of this squiggly line here as being the infinite sum. So that's kind of what this stands for in my mind. So I took this straight E here, sigma, which would have been like discrete piece by piece by piece adding together. And I said, because I'm having an infinite sum, I'm going to make it squiggly here. Then I don't have to worry so much about what I'm counting by, because I'm counting by this piece that's infinitesimally small. I'm going to consider the entire function, every possible input on the function. So my y value, or my height of my rectangle, is still f of x. And then this change in x, when this change in x goes to 0, we just represent that by a dx. And we represented it the same way with derivatives when the change in x go to 0. You can also just add in here the domain. So we start at A, we end at B. So this is just a different notation that's a lot cleaner to look at that represents the infinite summation.